and we reworked it so it can be used for more than with fingerprinting. So I will show you that. You can follow me on Twitter with the two names. Network Recon is where I will release the tool. So if you want to be informed of the release, you can follow Network Recon. So who am I? I have more than 10 years of experience in information security. Maybe I'm most well known under the handle Gomor. So that's my main portal around security is gomor.org. I also have a blog only in French, sorry, because I don't speak a word of Spanish. I prefer to say it. So if you have some questions at the end, I can't understand Spanish. So the blog is Protocol Hacking. I also started a web hosting company a few months ago, which is called SecureSci, only for French people. And my last project is about networkrecon.com, where I want to release as much tool as possible regarding network reconnaissance, which is a field I really love, because I'm a protocol hacker. I love to implement protocols. The most difficult protocol I had to implement was OSPF for open shortest path first. It's a protocol used in Cisco routers. And by speaking this protocol, you can inject routes in a whole network, so that's interesting to do man-in-the-middle attacks within a corporate network, for instance. So the subject of today is about NetSINFP, another Perl module. I have two big versions of this tool. When I say SINFP, I'm speaking about the old one, and when I say SINFP3, it's the new one with more features. And I also love FreeBSD systems and to develop in Perl. So the agenda for today, first thing, what is operating system fingerprinting? Would be quick. I will then speak about current tools and their limitations. So why did I develop another OS fingerprinting tool? And introduce the approach I had for SINFP, show the new matching algorithm for SINFP3, and I will do some demos before introducing the new architecture of SINFP3 and again doing some demos and conclude. So what is operating system fingerprinting? So my definition is the art of remotely identifying the nature of an operating system by analyzing how its TCP/IP stack is crafting network packets. So it's really how the bits and bytes are assembled by the stack. There is two main approaches in OS fingerprinting. You have the active fingerprinting, where you send some probes to a target, specifically formed probes, and you analyze the response to build a signature. So the analyst decides on the format of the request. It's very important. Compared to passive mode, where you are just listening to the network, you don't control how the frames are sent to the target, so you don't control how the responses are built also. And that's very important distinction between the two modes. And of course, these two approaches give different signature. We will see that. Sometimes I have the question, why not simply using banner grabbing for OS fingerprinting? I would say if you have the choice, you can more trust the banners than the TCP/IP stack itself. So if you have the choice, use that option. But it may be correlated with the TCP/IP fingerprint of the target to have more insight. So what is SINFP? So before the version 3, an operating system tool, fingerprinting tool written in Perl. So yes, for me it's the best language, that's my view. That's the language I master the better, so it's easier for me to write in Perl. It's module-based for integration in other projects. I really made a tool that way to help other people integrate it in, say, a vulnerability scanner or whatever. And it was the first tool to implement IPv6 fingerprinting, both active mode and passive mode. So you have the history of the tool. I will make a poll. Who has ever heard about SINFP before? 1 people, 2, yes, not too much. It is nearly 8 years old, this tool, so it's a long time. And in the past, it was integrated in the Backtrack Linux distribution, and it's no more integrated, so I don't know why. I hope, thanks to this presentation, the Backtrack owners will integrate it again. We will see. So, current tools and their limitation. So the most well-known tool for active OS fingerprinting is, of course, Nmap. I suppose everyone has used Nmap. So the probes used in Nmap, you see there are really many packets sent to the target. You have TCP SYNs, SIGs, ICMP echo request, UDP, TCP packets with strange flags, and all of that are targeted at different ports. For instance, you need to have 1 open port, 1 closed port, ICMP echo reply accepted by the target, and have 1 closed UDP port. This is many constraints. So problem 1 with this approach, what if some targets' answers are spoofed? Sometimes you have a filtering device in between that stops the packet and answer by spoofing the IP address of your true target, so you are fingerprinting the TCP IP stack of a device in between. And what if there is, yes, so you got different TCP IP stacks, yes, TurtleOS. This is one I really like. I don't know if you already had some strange results with Nmap OS fingerprinting, but when I see TurtleOS, I always wonder if I targeted a true turtle or if it's really an operating system. Problem 2, usually targets in today's internet conditions are really filtered, so you only have access to a few subset of Nmap tests because of filtering devices, packet normalization, and stateful inspection firewalls. So if you go back to the previous slides with the 15 tests Nmap is sending, with such a configuration, you just end up by being able to use 6 TCP SYN and maybe 1 TCP SEN, but I'm not sure this one will go through packet normalization devices. So, and problem 3, it's easily detected by IDS and IPS because Nmap is really verbose concerning how we craft its packets. So my conclusion is Nmap is really okay for land-side OS fingerprinting because usually you don't have filtering devices and all that stuff, but it does not suit anymore in today's internet conditions. But don't get me wrong, Nmap is still a wonderful tool for many things other than OS fingerprinting, and it's a must-have in your toolkit. But for OS fingerprinting, I think its approach should be changed. Regarding the passive fingerprinting tools, the best one is POF, written by Michal Zaliuski. And the latest version, POF-v3, is also doing passive fingerprinting over IPv6. It was not before. And it fingerprints TCP SYN packets and TCP SYNAC packets. There is no real limitation on this tool, but at the time of SINFP introduction, POF did not support IPv6 passive fingerprinting, so I added something in a lacking environment. The most important point for POF is that it has a comprehensive database of signatures. really, for me, it's the best tool in this category. But I will continue to try to improve SINFP3 passive engine because, well, I like it. So, previously I spoke about Nmap. The philosophy behind Nmap for active OS fingerprinting is one target IP address as only one operating system. In SINFP, the philosophy is different. It's one target plus an associated TCP open port as only one operating system. So the idea of that is that when you are port redirection or stuff like that, you can fingerprint another target than the IP address you see. So you can fingerprint protected systems thanks to that. And the idea to choose the test to run against the target to have the fingerprint was that every probe must generate an answer from the target. That is, we must evade filtering devices that could spoof the answer. And of course, the probes must reach the target, so it must evade also IP filtering or, more importantly, stateful inspection firewalls. At the end, we come with 3 TCP packets, all targeted at the same open port. One is a TCP SYN with just one option, the maximum segment size TCP option. In the previous version, this option was missing, and in some cases, targets would not answer to this probe at all, so it was not good. So thanks to that, every target is answering to this first test. The second one is the most important test. It's a TCP SYN with many valid TCP options. You have selective acknowledgement, window scale, TCP timestamp, NOP options, many options. And the last one is a TCP SYNAC. Well, I wrote mostly used for LAN-side fingerprinting because, as I said earlier, in today's internet condition, with a stateful firewall, the SYNAC will not reach the target. So it's okay to have this third test when you are fingerprinting from the LAN, but there is an option to not use it when you are fingerprinting over the internet. So another important point is that one operating system has only one signature in the database. The problem also with Nmap is that if you customize your TCP IP stack, for instance, it will change the signature of your system. And the approach of Nmap was to add this specifically changed signature in this database. So you come with something like 2,000 signatures in Nmap with fingerprinting database, which is quite huge. And I'm not sure there is so much operating system in use in the world today. So the matching algorithm has to take care of this potential customization of TCP IP stack. I will speak more about the matching algorithm later on. And yes, usually during our tests, only one TCP packet is enough to have a very reliable identification of the target. It's the second test, the one with many TCP options. Concerning the passive fingerprinting of SINFP. In the past, it was doing also fingerprinting of SYN packets and SYNAC packets. The trick I used was to use signatures taken actively. I did not have different signatures for passive mode and for active mode. So I simply listened to the network, gathering all SYN and SYNAX packets, and applied a transformation on this packet to make looks like they were acquired in an active mode. So I could use that to match, again, signatures taken in active mode. So it was one signature usable in active mode or in passive mode. Well, I thought it was cool, but in fact, it was a failure. the problem is, as I said earlier, you don't control in the case of SINAC fingerprinting, you don't control the first scene. And the SINAC is built compared to the scene. So if you have, say, an embedded system with a really small TCP/IP stack with no TCP options implemented, if this embedded system is connecting to a target, the TCP scene will be really small, and the SINAC you will see on the network to perform passive fingerprinting will also have very few TCP options. So in fact, if you want to have a good passive signature of all TCP SINAC packets, you have to send as much as TCP scene as possible to the target to generate your database. Basically, say you gather the TCP scene as built by Linux. You do the same for FreeBSD, SunOS, an embedded system, all that. Then you send all the scene to the target you want to add in your database, and you may have all possible SINAC packets for a specific operating system. This is an approach taken by POF v3. So in fact, when you use POF, there is a small tool to send many TCP scene to a target to help add that to the database. But the problem I see with that, you won't be sure to have all the possible methods for crafting TCP scenes. You can't do that for every operating system. But this approach is efficient, so it works okay. But I preferred for SINFP2, SINFP3, only fingerprint TCP scene packets, because it is easier and sometimes I'm lazy. So yes, I said it, only TCP scenes are fingerprinted. Yes, for SINFP3, now I have completely separate passive signature. So I have active signature in one side and passive signature in another side. As you can see, there is only 21 signatures in the passive database, so I need contributions. So if you can send me scene packets in backup files and telling me this is this or this operating system, I would be happy to add it to the database. Regarding the active signature, this is nearly 300 signatures, and I consider this database to be quite mature right now. So. Sorry. So I will take an example of fingerprinting with Nmap. So against one of my server. And you see the possible operating system found by Nmap. It's FreeBSD 7x or 6x or 8x. But there is a bug here, because as you can see, I put in bold, you see only 7x or 6x at 98% confidence. And you don't see the 8x at 98% confidence, so there is a bug in the output. So in fact, Nmap is thinking it's a 7x or a 6x. Now with SINFP, I hope it's quite readable. Well, I will do a demo, it will be easier. And with SINFP, you see every potential operating system with a match score. You see there is multiple possibilities with a match score of 100%. And the tool thinks it's either 7x or 8x. And the good answer is 8.3. In red, this is what I call deformation masks. It's used in the matching algorithm to take care of the deformation that may be involved because of filtering devices. I will explain that. So, SINFP3 matching algorithm. I will take as an example a signature, an active signature. You have the three probes, well, in fact, the responses to the three probes, S1, S2, and S3. and for each you have 5 elements. The first one is what I call binary flags. It's a comparison between some headers of IP and TCP between the request and the response. In the past, it was really binary. It was 0 or 1. But Nmap has improved its OS fingerprinting engine a few years ago. It's its second generation. And I took some comparison it was doing. So now you have 4 values possible, 0, 1, 2, 3. It's no more binary, but I kept the name for, I didn't want it to rename all the stuff in my source code. The second field is, well, TCP options, TCP flags. I decided to put it as a signature element because, well, maybe some system will answer with more flags than just SYNAC or RST. We don't know, we see strange things sometimes. The third element is the TCP window size. It's one of the most important elements. There are many possible values for this one, and your usual operating system is using a different value. And the most important one, TCP options. So, how does that work? I simply copy and paste TCP options from the packet, and values that may change, like timestamp, it always changes. I fill it with FFFF, so it's easier to match it in the database with the matching algorithm. And some values, I extract them. So you see 02, 04, FFFF. This is the maximum segment size option. And it is moved to another field. Same is true for the TCP window scale. And, well, I said some systems do strange things sometimes. For instance, HPUX loves to add a string, no TCP, in its RST packet. So it gives a strange signature like that. So the maximum segment size is in its own field. And thanks to that, it's easier for the deformation masks to apply and be able, if a device is in between has reduced MTU, for instance, the classic default MTU size is 1460, and the MSS is the value of the default MTU, but sometimes an MTU is reduced because of a specific link connection, and thanks to that we can accept different values and still match the operating system, importantly, before adding a new signature to the database. The window scale, same problem, extracted from the TCP options, so you can write deformation masks for the window scale also. Finally, the length of TCP options in bytes. I'm not really using it, but I store the value if I want to improve the matching algorithm, if I have a bright idea someday. So, complete example of SINFP signatures. The first one is IPv4 active signature for a FreeBSD 8.3 system. The second one is for the same system but in IPv6. You see in red and yellow the differences in the value. I spoke about the maximum segment size. You see there is a difference of 20. But besides that, in some binary flags, it's nearly the same signature. We will see why it's important. In passive mode, IPv4, here for Windows 7 system, you see there is no more the binary flags, because it is a comparison between a request and a response, and you don't have that in passive mode, so you can completely remove it, and you have a signature. You see same problem with IPv6 signature. The MTU is reduced. So I don't know why IPv6 impacts the size of MSS. The matching algorithm. We have 3 levels of heuristic. The first level, It's a perfect match. The value was not modified at all, so it's okay. The heuristic one accepts some minor deformations on the packet. And the second one, it's major deformation, but in fact, we can completely ignore a parameter because, well, in the current context, it is of no use and it does not help you identify a stacked operating system, so you can match with the heuristic 2 mode. And so these deformation masks are really important for the matching algorithm because this is what takes care of devices modifying the packets with reduced NTU or stuff like that. Modified window size, deactivated TCP options. You see an example of a signature completely written in heuristic 1 mode. And as you can see, it's written with regular expressions. For instance, here, 01 with question mark, it just says this option may not exist. So if it's not there, the algorithm will continue to match the signature. But the matching score will be reduced, of course, because of the deformation. An example of a non-deformed signature. So this is the reason for this long string BH0, FH0, all that stuff. It says we have matched in perfect condition. So now, the same target scanned from a different network with a modified NTU. So you see the match score is now 98% because the NTU is lower, but it matches with the heuristic 1 regarding that value. But you still identify the system without adding another signature to the database. So each element has a weight. The less deformed the element, higher is the weight. In heuristic 2, the weight is simply 0. It does not help you, so it does not continue for the matching score. And most discriminant elements have higher weights. For instance, TCP options and window size, it's the most discriminant element, so it gives many points for the matching score. Yes. How the lookup is done in the database. Basically, you find intersections between all these signatures. You take the S1 and you search all the ID in the database that can match all the 5 elements of S1. Then you do that for S2, you do that for S3, and finally you have 3 circles, and you try to find the intersection between these 3 circles. If there is no match, you do that, but only for S1 and S2. If there is still no intersection, you only take S2 because it's a better test. And for hypothesis, it's exactly the same algorithm. Of course, signatures are very similar, but something is a little bit different. If you don't have the signature for an IPv6 target, you can match it against IPv4 signatures. So this works really great. You have only 2 to 3% difference when you do that. So even if your signature database is not complete, you can still identify the target. And for passive fingerprinting, same algorithm against passive signatures. The database, it's SQL based because it's easy. Everyone knows SQL, so why creating a proprietary database? So I get the number in the database previously. I don't integrate every signature. I must trust the signature because sometimes I have a contribution. But I see that clearly this signature has been modified by a device in between. So I can't add it to the database. I only add signatures taken in perfect condition. Usually, the operating system is running in a virtual machine with no filtering devices, no packet normalization, nothing. and I add that to the database. I keep all PCAP traces, so I can regenerate all the signatures if I want. I can work on another matching algorithm and test if it still fits. I can do many things with it. And that's really a good database of SIN packets. I have SIN packets for passive mode, but I don't have many for that. But for the active mode, I have many PCAP files. For passive mode, yes, I need contributors, so don't hesitate to ping me with SIN packets. Demo 1. Okay. So, what I will do is to scan a C class. I will do it in live, so I hope it will work. Okay, demo 1. So how do you call the tool? Is it begin off? Yes, I suppose. SINFP3 -target, the network you want to scan. In previous version of SINFP, there was no SIN scanner. You just had to put one IP address and one open port. That was just what you could do with that. Now there is many options. You could scan and enter a C class or whatever. Specify more than one open port. Here I put one open port because it would be quicker. So verbose mode. Active 2, I spoke about it. It's to send only the 2 first tests, because over the internet the SINAC will probably drop by the target, so you accelerate stuff by using this parameter. Threshold 80. I don't want to print signature with a match score below 80. So first step, SIN scan against the C class. It takes a few seconds usually, except if my Wi-Fi connection is broken, which seems the case, like in all demos. Yes, okay. So, you have many outputs for the tool, because I put verbose 1. And it's still lagging. Okay, yes. So here you see one of the targets. Stop to move. Okay. You have the put. Well, the internet connection is really shaggy because I don't have a response for the first test. That's really strange. But you have a response for the second test. And you see it's still matching at a 98% score for either a Linux 24X or 2C6. Well, I put in parentheses the exact version, but for me, OS fingerprinting can determine the exact version. You just can determine the family, which is usually good enough. So this one, no answer to the S2. So we have Linux, and here you see Linux 32X or 30X with 98% score. So I will stop the demo here for this one. So default modules used in SINFP is to SIN scan the target, to use the SINFP3 database of fingerprints, to use the active mode, so the search module is also the active search, and to output results on the console. We'll see more output modules. So the architecture is now plugin based to be more modular. Usually, if you want to take input, say from the file instead of from the command line, you can write an input module that will read the file, analyze it, and feed the engine with whatever you want the source to be. And improvement on the matching algorithm. Previously, the deformation masks were written manually. It was quite tricky to write it because I had to test it and see if it was performing well in the field. So it was not really great. So I modified the matching algorithm to try every combination and to output a score. So the score is also easier for humans to understand the result, because not everyone is familiar with deformation mask. So the first probe has now TCP option. The passive mode is autonomous, 10 minutes. We need to go quickly. So, and plugin based, of course. So the global architecture, you see you have an input module which generates next objects. It's intermediate objects you can feed to the mod. The mod then feed the search engine, which just look up in the database and finally outputs result objects. So you can display it in whatever way you want, on the console, on a CSV file, XML file, whatever. So you have many implemented modules right now. I will go quickly. Yes, I will speak more about the scene scanner. It's written in per-XS. For those not familiar with per-XS, it's really near C language for performance reasons. And it's efficient enough, I consider. For instance, you can scan a C class in 20 minutes for top 10 ports with a default configuration of 200 packets per second, and 3 tries, it's around 10 kilobytes per second. It's the default configuration. You can specify more packets per second if you want. It's a KISS algorithm you choose. TCP packets are written directly at layer 4. No need to bother with crafting IP headers. Let the system do that. We don't want to spoof IP addresses anyway. And it uses the SINFP magic SYN packet. The input connect module is interesting. It's like my old passive fingerprinting failure. But this one, it works only from Linux, because Linux TCP SYN is the same as the one in active fingerprinting. And in fact, you simply do the TCP connect to the target, listen to SYN and the corresponding SYNAC. And thanks to that, you can generate the signature of the target and match it in the database. It's really effective when you are from a Linux system. And it's no IDS will bother with telling we are fingerprinting, because it's just a TCP connection to a web server, so no problem with LDSs. It's a really stealthy approach. App Discover, it's quite interesting. You are on your LAN and you want to fingerprint all your LAN hosts. So you use App Discovery, you send app requests to all the IP addresses of the network to find live hosts, and you perform active fingerprinting on them. And for IPv6, I use a trick. You do the app scanning for IPv4 addresses. You have a list of valid MAC addresses, and you apply the EUI64 transform against MAC addresses, so you have FE80 IPv6 of your packet. So you don't have to scan the FE80/64 to find the targets. So demo 2, this one should work. So the idea, to launch the tool, you use the input app discover module. I will not do it because it will take too much time. You output the result to pickup files, so you can replay it with the second command line here. So you gather all pickup files. You can output it as a CSV file, threshold, we've talked about it. And finally, we use the CSV file to output the results using ubigraph, which is, I will deactivate an option because it's too slow. So as you can see, you can visualize your home network in a wonderful 3D manner. There is colors. Blue is for Windows systems, red for BSD systems, and green for Linux systems. In fact, every node is one open port. I can display the label, but it will be very slow, so I don't show the label. So this is an open port every time. So I don't have time, so no demo 3. But it's the same thing with many nodes, basically. And with such many nodes, it's over the internet, you can really see some target with port redirection. So the nodes may be from different color for the same IP address, but well. So, conclusion. I tried to make many improvements on the tool. The matching algorithm, mainly. It's better, you have a match score. So that's good, human can understand easily if the tool is confident or not on the fingerprint of the target. The architecture has been completely rewritten, so you can write your own input modules or output modules, mainly, to store results in a database if you have a database. That's really awesome for scanning the internet. And in fact, I didn't say, but the input module gives next objects, and each next object is forked, so it's a parallel scanning engine. There is a flag to specify how many jobs you want to do in parallel to speed up the things. So improvement on the passive fingerprinting also, but for me it does not compete with POF today. And many more features. A plugin to add signatures in the database. Previously it was hard to add signatures. Mainly I was the only one being able to do that. Now there is a tool, so everyone can do that. A flag to update the database. It downloads the file from the internet, verifies, checks them, and if it's newer, it updates, stuff like that. Logging modules, and you can design your own modules right now. That's a cool feature, I hope. So to get informed of the release, probably today, you can follow Network Recon, and I will tweet about it when it's released. Questions?
¿Alguna pregunta? Bueno, muchas gracias, Patrice.